let's go back to this geospatial adventures thing. So it's pretty straightforward to find the amenity called pub in Sweden. And all I've done with the code from Biergarten in Deutschland, Germany, is I just changed the ISO code to SE for Sweden, and then the amenity of interest to pub. So node, way, and cell, these are sort of JSON details. It's not going to be on the exam, but the node, way are specific ways the OpenStreetMap addresses or tries to represent the map. Okay, node is just a point, like a node in a graph, and way is basically a collection of nodes, right? So way is like a polyline. So all they use is points and polylines pretty much. And then of course there's a lot of metadata on what's a pub, what's a church, and all sorts of things. So this is kind of the base layer on which you would build some kind of a service that provides users something, a value based on maybe their own historical behaviors and so on, right? So, okay, so this is just for fun. So interestingly, the pubs in Sweden, pubbar i Sverige, are way less than the beer gardens in Germany. I'm not making any, but you can clearly see Stockholm, Malmo, and Gothenburg. So that's that. So the next thing, so this is in the updated notebook. So the next thing I wanted to quickly go through is just a few extra things from yesterday. So I was being a bit slightly sloppy on the Wiener process. So to properly understand so we were talking about simple random walks yesterday. So I also learned at the student faculty meeting about the course from someone in economics that you will be learning something called autoregressive processes after regression. So this is important to bear in mind. So a simple random walk is just, you usually do something symmetric, and you can do these walks in ZD, as I showed yesterday. And then I said that a formal mathematical scaling limit of this is called the Wiener process. And the Wiener process is extremely important. It's the Brownian motion because it forms the most important element in what's called stochastic integration. Stochastic integration is a generalization of classical integration you learn, and that's fundamental in financial mathematics, stochastic control in engineering applications, and ways of ensuring that your systems are robust and things like this. So we won't go into these things, but just what is the connection, everything you've learned to this. So what we're going to first do is simulate an independent so-called Rademacher random walk in Z, integer lattice. And then we're going to do it over discrete time, right? So discrete time in Z plus. So Z plus is nothing but 0, 1, 2, 3 discrete steps. Okay, we start at time 0 and step increments. Okay, so now what is actually a Rademacher random variable? It's actually a very simple one. It's just this guy here. So we call capital K the Rademacher random variable, and it has this probability mass function. So if the probability half, it takes -1, and with probability half, it takes +1. So it's all just a bit flip, right? Yeah. So instead of Bernoulli, which is 0 and 1, this is -1 and 1. So if we take this Rademacher random variable and simply start doing our random walks based on this, then we can easily obtain scaling limits in this Brownian motion. So I've given you a very quick thing here. So U's are just, so I take random, which is uniformly distributed between 0 and 1. I subtract half, right? So I just move 0 to -half. So everything is now uniformly distributed between -half and half. Okay, that's all this is doing. And then once I've done that, I take the sign of U. So sometimes it'll be less than 0. Half of the time it'll be greater than 0. So the sign of U will give you plus and minus 1. That's it. So you can just go from random, which we did yesterday, to Rademacher. So here's some samples, and here are the signs. So once we have Rademacher random variables, we can simply compose them and get simple random walk. Okay, so here's just an interact. You don't have to understand the details, really. It's quite straightforward. You've seen this, but just pay attention to these paths. So now I'm, starting here, and I'm going up, and then up again, down, and up, and so on. So now time, discrete time, is on the x-axis, and the position of the random walk on the integer lattice is on the y-axis. Right? So you can, you can increase the number of steps taken by the walk. So it's the same walk that's continuing, right? So the initial part we did is the same, and so on. So this is kind of an important thing, because if you think about it, let me do new random walk every time. So let me just do 267, maybe. So now I'm getting completely new random walks every time, right? So I don't know. So for example, Donald Trump will say the carbon dioxide concentration we looked at from Hawaii is just a random walk, right? Because if you just do a random walk, it can keep going. It's possible. So if I do a linear regression on it, I'm actually violating certain assumptions of simple linear regression. Right? We may not cover that, but I think in your economicum next semester, you will start studying those kinds of processes, those called autoregressive processes. But it's always good to know what random walks do, and you can build a lot of intuition from this. So of course, when we keep increasing this number of steps to be very, very large, and then rescale it, okay, this divide by the number of steps at the right rate, then you get Brownian motion, right? So if you read Einstein's original paper in the 30s on Brownian motion, it's pretty, he's not using math, he's talking to you, right? So this is, but yeah, it was formalized a bit later by Wiener. Okay, so now simulating an independent Rademacher random walk in Z3, right? Now three-dimensional walk, so go up, down, this way, that way, this way. So it's just a generalization of Rademacher in Z3. Right? So it's the same idea. I'm just, the code is now super simple. You just have, if you use NumPy, it's actually, yeah, just points and just list comprehensions. There's nothing going on. So here is the three-dimensional random walk, right? You can increase the steps and see. Okay, what is the point of all this? So the point is, these are the building blocks that, for example, physicists who study diffusions will use, but more from applied statistics angle, people or statisticians who specialize on deciding how a particular state or a nation, like a sovereign nation, negotiates with another nation that's producing pollutants, right? Greenhouse gases, all sorts of things. So this is a very interesting problem, right? So this is, of course, just a random walk. What you would add to this is drift. You would have weather models that'll add certain drifts from predicted weather patterns, yearly patterns, and then you will get a pretty good estimate. For example, if you couple that with meteorological models and watershed models, that's how you basically get to how much acid rain is possibly being caused in, say the lakes of some part of Sweden. I don't know. Sweden is not that polluted, right? Because even the Scottish guys buy your wheat from northern Sweden because it makes better scotch. Not yet, but this is a serious problem. Eastern Europe, U.S. East Coast, India, all over Asia. It's a real serious problem. So anyway, this is just to give you some insights about why, what I mean by simulation-intensive inference, right? So you couple simulation with some other models. And so this is something I went through yesterday. This is mainly to, I told you I was doing this stuff with the Israelis, and here we have, this is just now trying to do multiple independent random walks. So each person, each walker is an individual, and in this case, my innovations are not Rademacher. I'm sampling, I think, Gaussians or something. So you can change how you, I'm actually just sampling, what am I doing? Yeah, I'm taking random, so some uniform 0, 1, multiplying it by 2, and then subtracting 1. So you can do whatever you want. The innovations can be Gaussian, and of course, if you're if you're, if these individuals are moving on roadways, then you would ingest OpenStreetMap, turn that into a graph, and do simple random walk on the graph, right? So you conform to the geometry of where the walkers are going, and if it's a motorist, you'll have speed limits, and then if it's a pedestrian, and so on. So this is kind of, you have all the first principles to do these kinds of things with a little bit more work. Okay, I want to also give you something super concrete, so we will make mathematical sense of why this is justified for simulation intensive inference, right? So here, I'm just going to show you, so I made a very simple 2D random walk. Here, the increments are not Rademacher, right? I'm taking random minus half, so I'm sampling uniformly from minus half to half, but then I'm multiplying the whole thing by 0.05, right? So it'll be samples uniformly distributed between negative 0.05 and 0.05, okay? Tiny little uniform distributions around 0. So that's my innovation for 0.0 and 0.1, how I move. And then I'm just appending and I'm getting a path. This is what I mean by a sample path V of length n taken by 2D random walks with scaled uniformly distributed increments. Just two. So now what I want to do is I want to actually use this walk, right? But not just one walk. I want to have multiple independent walks. So I create a list called empty list called walks, where I'm going to store multiple independent walks. Then what I'm going to do is just, so I have this little problem, right? So the problem is actually a baby example of what's called a rare event simulation. Right? So rare events happen. When rare events happen, usually somebody has to pay insurance, for example, in the insurance industry, and you want to really have a pretty good understanding of the probabilities of certain rare events, right? They cost a lot. So insurance premium calculations is a huge industry for this. Okay, this is a silly example, but it's the same idea. Suppose I have a random walker here, right, with this very simple model. It could even be Rademacher. And once you have, slight complications, it's very difficult to do anything analytically. So what I want to do is I want this random walker to start here and move around in this independent way. And I'm interested in the probability that the random walker will touch this circle. This is some region of interest, okay? So what is it? What is the probability this person will touch this circle? And after having touched that circle, what's the probability that they will touch that circle? Right? So this is already complicated to do analytically, once you start changing the innovations of how they walk and stuff. But you can do this very trivially in simulation, right? So what you do, you just start a whole bunch of independent random walks here. So I've done 3 for you. This guy, the first guy, moves around and boom, touches it. I'm controlling the seed. It took me a long time to come up with this picture. The second guy starts. Okay, so the first guy is frozen. The second guy starts and kind of wanders off here. And then the third guy is sort of, wanders, I don't know, does some turn, wanders off here. So only 1 out of 3 touched this, okay? So of course, if I make the number of random walks to go to say 1 million, do this super fast, parallel, whatever, then the fraction of guys that touch the first guy is an estimate of the probability, right? That's how we motivated probability for axiomatically. Now, as long as the pseudo-random number generators are good, right, then we can actually apply probabilistic theorems you will see in 2 notebooks formally. But just for intuition now, so now the nice thing is, so 1 out of 3 touched here, then I can play the same game independently from that guy. So again, start a whole bunch of random walks from here, right? Maybe only 1 out of 11 will reach there or something, whatever, some fraction. Then you can multiply those probabilities, right? So it'll be 1 out of 3 times 1 out of 11 and so on. So in true rare event simulations, these things will be like 1 out of, I don't know, 10 billion or something crazy like this, right? And then you multiply that again, right? So these are some examples, concrete examples of how you turn your simulations into probability estimates that you cannot do analytically. Yeah, I mean, only if you really know what you're doing with your machine, you can turn these things quickly into animations, but you need to, do some image magic stuff. So it's just for those who want to do this, because turning this into an animation is actually not too hard. And then for presentations, you may want to do, it's a good idea. Okay, so let's continue here. So we were looking at the Immersion Sampler yesterday, right? So this is now the whole point of this notebook is how do you systematically convert or transform samples from the uniform 0, 1 random variable into samples from any other random variable, right? Well, yeah, at least invertible ones here. Okay. So we saw this yesterday, and then we talked about setting the random seed, right? Just like in a linear congruential generator, you set the seed and you can control the simulations. So you guys know about iterators, right? And generators. Some of you are staring at me. So, I mean, one of the complaints was that the assignment 1 was too easy, so assignment 2 won't be, I think. So it's good. I mean, you don't worry. It's like equal weighted, right? So even if you completely bomb it, it'll be okay. So for example, you know, maybe in assignment 2, I will ask you to implement a linear congruential generator as actual using generated expressions and as an iterator, not as a function, right? So you don't use return, you use yield and things like this, which is how actually this random is defined inside the machine, right? So you already know about iterators from before. If you missed or didn't show up, you can read about it, and then maybe the assignment will be implementing the linear congruential generator not as a function but as an iterator. Anyway, so that's what's really going on here. So you can, that's why when you call random again and again, it'll remember the current state and then produce the next state. Okay, and this model of computation is called continuation. Okay? Continuation model, because yield just says, well, stop wherever you are, hold your state, and return, right? And then it has a method implemented called next. So when it's called again, it'll know where it is. It'll call the method next and tell the answer. Right? So that's how the random number. That's why when you control the seed, it has to be in the beginning, and then it just continues. The whole process continues from that seed. Okay, so so this was the point here. So let's maybe restart the kernel. So do you guys know these kinds of things like, so let me just, so run all above. So for example, if you go to File and you say New Notebook, right? You know how to create your own new notebook. You played around? No? I thought you guys are like really young, so you play around. Like my daughters go crazy on the laptop. I don't know. Like after a while, like what do I do? So anyway, just play around. You cannot really break anything, you know. So I mean, for example, this is SageMath, you know, 8.4, which is you know, so that's the notebook we are using. You know, SageMath 8.4 is our kernel, right? So you have multiple notebooks and of different kernels. GAP is something for your maths and algebra. Python 2, for example, is something. If someone is, if you're taking a course that's pure Python, say Python 2. I'm sure in a couple months Python 3 will be an option here too. Then if you just go, you will get a pure Python 2 notebook, which means you cannot, you know, you won't have this, you know, if you say a equals 1, you won't have the SageMath integer rings thingy. You'll just have the pure Python int, right? So this is kind of a nice place to play. Okay, so let me just go back. So then let's, so the point here is that depending on which seed you start, you get different sequences. So you superimpose here. Some of this is like repeating from before. And we already looked at Bernoulli theta random variable when we were doing these simulations. All we really were doing is simply, so here is just probability mass functions, CDFs, and so on. And then we saw the interactive effect of changing theta. So then the distribution function is the main thing to look at. So the uniformly sampled numbers are between 0 and 1. So all you do is whatever they happen to be, you invert it, right? And when you invert a discontinuous distribution function, it's defined so that you just pull down this way. So all the numbers that land between 0 and 0.5 will go here, and everything between 0.5 and 1 will go there. And of course, when theta is not 0.5, so this is too big. So let's say it comes up heads all the time, then you see only this fraction of uniform numbers will end up as tail, and of course the larger fraction, the right fraction, will end up as heads. This idea is essentially, it's the main idea. And so we were looking at this. We saw floor yesterday, and then this was the pseudocode. I looked at U is uniform 0, 1, X is this floor of U plus theta, and everything simply works by just a pure list comprehension of the random U's we simulated. And this is simply going through the same idea through this inversion argument. So here we just looked at having lots of samples and looking at the empirical frequency. So the empirical frequency is close to the true theta that we're simulating from, and so is the empirical distribution function as we increase n. So is it clear what EP, MF, and ECDF are? Empirical probability mass function and empirical cumulative distribution function. Just the frequencies. Okay. So now, so we just have the same thing. You can play with this. This is a U-try. Then we looked yesterday at equiprobable de Moivre theta random variables, or just 1 over k, 1 over k. So when for equiprobable de Moivre, or rolling some fair convex die, you have probability mass function and distribution function like that. And then I just said all you have to do is take U, stretch it by k, floor it, and then add 1. Okay, so that'll give us what we want. This is the pseudocode for it from yesterday. So now, okay, so, and once again, the interact is just for simulations. Okay, so ceiling is just the smallest integer larger than whatever you're passing in. So ceiling of 3.8 is 4. Okay. This is exactly where we were yesterday, Immersion Sampler for continuous random variables. So what is the main idea? We take exactly the same that worked for the discrete, and we do the same thing for the distribution function. So if I have some distribution function like that, then I just take whatever the U is from the random sampler and I just invert it. So this gives me my X, F inverse of U. Right? This is F of X. So that's it. And this is essentially a proposition or a theorem. It just says that if the distribution function, capital F, is continuous with density F, and if its inverse is defined this way, F inverse U is the infimum. Infimum is essentially a minimum. It's a slightly more, so it's basically the infimum of a set could be the could be an element that's just below every element in the set, but may not be part of the set. So it's almost the minimum. So infimum of X such that f of X equals U, that's the definition of the inverse. And then the proposition is that then f inverse of U has the distribution function f. Right? So provided U itself is uniform distributed. So this is kind of, I mean, the proof is literally this one line. It's just passing sets through. Just definition of probability is all we are applying. And this gives us something called the Immersion Sampler. So it's a very generic algorithm. And as long as you can invert the distribution function, you can, and produce samples from uniform 0, 1, you can produce samples from whatever this random variables distribution function is that you can invert, right? So here is the idea. And this is what we've been doing in the examples before already. So we have a PRNG and a procedure to give us the inverse. The output is a sample X from random variable X, distributed according to capital F. And then the steps are just draw U, calculate X, F inverse of U, return X. So this is essentially what we did in the walk, in the simple random walk, when we, subtracted half, and we were now simulating from a uniform half minus half. So when I did the Rademacher thing, the first step we did was take a uniform. So this is like theta 1 in this example. This is theta 2. And that's what we did, right? We took U, which is uniform 0, 1. And then we just multiplied or subtracted half. U minus half. So now U minus half, say X is that random variable. So now, so use from rand, step 1, step 2, and we're done. So this is basically the probability density function for uniform theta 1, theta 2. You've seen this. And the thing is, we also want to look at the inverse. Right? So the inverse now, I'm showing it the other way. So any random number here gets inverted. Let's flip it around. Okay, so here is the PDF and CDF for uniform, and in this interact, we can just see for different values of theta 1 and theta 2, you just change the line. So then simulating from the uniform theta 1, theta 2 is just this basic idea. So you take U, go this way, or take U and go this way. Okay. So here is uniform F inverse. So this is our function. And you see all I'm doing, everything is here. So I take theta 2 minus theta 1, the width, multiplied by U. U is always scaled between 0 and 1, so it's unit interval. So you scale and you shift. Is this all too easy? Boring? So, like people have been writing emails. I know we're live, but it really doesn't matter. When you write emails, just know that if you are sort of upset, it's better to talk, and because it's a public document. It's not good for, it's a public document, right? When you write an email, I'm a public servant of the Swedish state. So, so some people have been asking, like, why are we doing this? Why are we doing math? Is this stats and all of this? I don't know. I mean, I tried to reply nicely, but I mean, I'm not like some guy off the street, right? So I am just to, I don't know. I don't want to like show off here, but I'm a, associate professor here, and it's with specialization in data science. I'm also a consulting principal data scientist at Combient AB. I run a bunch of meetups here. I coordinate an industry academia center. I don't know. I've started my own company, sold it, and I've been chief analytics officer of my own company. I worked for startups that sold software to U.S. security, competing with U.S. security agency. So I know a little bit, right? I mean, so the reason I'm giving the course this way is because that's what I think, your learning outcomes will be met. But you need to have sort of foundations that are not too deep, but just right enough in all the areas so that you can think for yourself, because that's what you will, when you go for a job, it's the technical interviews and all of this. I don't know. So I think I'm doing what what I believe is best for you. But please complain, when the course is over. So, or or if you like it, say whatever. So that I don't want to. Yeah, it doesn't matter, right? It's your life at the end of the day. You can always do some other course too. So anyway, but let's continue. So. Yeah, so here is a uniform sample, and this is a function to simulate samples from the uniform distribution. So we now generalize this. So the point is theta 1 and theta 2 are parameters. This is a parametric family of uniform theta 1, theta 2 random variables. And now this nice function generalizes this, right? So for any theta 1, theta 2 you give me, I'm going to just do your comprehension, and I'm going to apply the inverse and return that. So I've kind of coded this up. So now this is the sort of, we're starting to move into inference land slowly. So I'm going to think of parameter 1 as -5, parameter 2 as 5, and then the number of samples to generate is 30. And then I'm going to create my variable. My uniform sample is uniform sample number to generate parameter 1, parameter 2. Right? And I'm printing this. So this is kind of like simulating data from a known distribution, right? So this is very important because later on what we will do when we understand estimation is we will simulate data like this, but then we will pretend that we don't know the true parameter, or at least we won't show the algorithm that's trying to guess the true parameters. We won't show that algorithm this information, okay? And then we will find out that certain estimators will recover the true parameters no matter what it is, right? And that's the theorems we will see soon. These are the law of large numbers and the central limit theorem. Okay. So here we just have an interactive function to plot samples from the uniform distribution. I mean, it's just, so here are my samples between, say, 0 and 1, maybe between 0 and 2, and I'm just plotting them one at a time. So when we did the innovations, this sucks. This is not going below half. Right. Let's see. Theta 2. So let's make this. See if this. I don't know. Okay, good. So when when we did this little random walk, so what we did was -0.5. Pretend it's -1. So now I have uniform samples of -1, 1. We had a -half, but doesn't matter. So when I was doing my random walk, I was at 0, 0, right, or at 0, and then I chose my first number here, which is, and then I do my innovation. So it's basically the cumulative sum of this sequence, right, is actually a random walk with this kind of uniform local jumps, right? So, okay. And then your Rademacher is different, right? Rademacher is half, with probably half it's -1, and with probably half it's +1. So we're now doing the uniform one. So in the Rademacher world, it'll just be like jumping between -1 and 1. So that's the simple random walks you saw. Okay, so what is this? The normed keyword is deprecated. The normed keyword keyarg is deprecated and has been replaced by density keyarg. So let's fix this. So this is density. Okay, so there you go. So if software evolves, right? This is the whole point. So a lot of this content, if I teach this again next year, will kind of change, right? Python 3 will dominate probably next year. So anyway. So yeah, here I'm just basically looking at a histogram, right? This is, remember I told you, let's increase the number of bins and the samples. So what have we done? We've taken pseudo-random numbers that are uniformly distributed in 0, 1, and then we have transformed them. Here it's a simple thing, stretch and scale, stretch and translate. And then, so we want to see if the histogram looks like we would expect of a uniform sample, right? Finite uniform sample. So, if I increase the sample size, hopefully it'll be more and more leveling off, right? Whoa, that's cool. Anyway, exponential lambda random variable. So this is now going beyond just stretching and scaling. Right? So the exponential lambda random variable is extremely important. It's our memoryless random variable in the continuum, right? So what is a memoryless random variable for the discrete world? Do you know what I mean? So there's some special random variables. Have you guys heard of the geometric random variable? Good. So let's go there first quickly, because these guys are unique. All right. So discrete random variables are basically, what is it? So basically there are so it'll have, say, finitely many outcomes, right? So we saw the equiprobable de Moivre, right? With k possible outcomes, but each of 1 through k is equal probability. But it doesn't have to be equiprobable, right? It just has to have k numbers that are non-negative, like 0 or less than 1 each, and of course they all sum to 1, right? So, let's say finitely many outcomes is one basic. So the de Moivre, the general one, actually is not just 1 over k, it's theta 1, theta 2, theta k, right? And these thetas are just, they have to satisfy the probability axiom, so the vector theta, right, is said to be an element of what's called a k simplex, right? This is the probability simplex. I don't know, sometimes k or k minus 1, so this is called the probability simplex. So what is this? So in 2D, it's this, right? X-axis 1, 0. This is 0, 1. This is 0, 0. So any point on this line is theta 1, theta 2. Right? So this one may be half. So this is called, I think this is called the 1 simplex. I always get this anyway, k minus 1 or k. So, right, this is how we talk about a de Moivre random variable with 2 possibilities. So 3 possibilities is just this. You guys already know linear algebra and calc in 3D, right? So this is 0, 0, 0, and this is 1, 0, 0, and so on. So this is the orthonormal basis, right? These corner points, 0, 1, 0. Right? So any point on this triangular plane is now a parameter, right? Okay. So usually we call this in the Bernoulli world, whatever. So we call this, so it's theta 1. And in this case, you see, it's 1 minus theta 1. So theta 2 is just, so that's why it's called, it's k minus 1, the simplex. Because there are only k minus 1 effective degrees of freedom because of the constraint, right? So here, theta 3 will be theta 1 minus theta 1 minus theta 2, right? So you can move around anywhere, but if for a fixed value, you induce a distribution, the de Moivre theta k, 1 theta k distribution, and then you produce samples from it, okay? So this is one thing. The other thing is essentially if you have countably infinitely many outcomes, right? So you know it's countably infinite. So for example, if I have all of z plus, right? So say 0, 1, 2, right? So this is the non-negative integers. So if this is all possible outcomes, I'm in a different world, right? Because I I cannot really, I cannot afford to have, a uniform distribution, right? So uniform distribution on, so this is your de Moivre. Let's start like this. 1 over k, 1 over k. So this is a uniform distribution on k outcomes, right? That's a special case, de Moivre. And then we generalize de Moivre. Now, both of these are just in this world. And remember, when k is like the Mersenne prime or whatever, right? Huge number, right? K is our modulus. So pseudo-random numbers are in this world, you see? Because they are just very, very large k, and we just take the entropy, the uniform distribution there, and then we transform it formally. But when you have countably infinitely many outcomes where this is actually going to infinity, right? We cannot have a uniform distribution, right? Think about this. I mean, can you roll? And it's no friction, right? Because when k is finite, right, the number of sides of this polytope, whatever I'm rolling, is going to be finite, and it'll come to rest. But if it has countably infinitely many sides, it's a different game. Right? You cannot define. This is convergence of series, right? You cannot have a constant number that you sum infinitely many times equaling 1. Possible, right? Intuitively. So now, which means we have to allow probabilities of infinitely many things to get smaller and smaller. So everything you learned in Calc 1 on convergence of series, all of that comes to bear here now. Right? So one of the most important ones here is the geometric random variable. So geometric theta random variable. So what's the idea? I'll stop after I just quickly construct this. So you're doing a coin toss, right? Head, tail, head, and so on. So let's say head is 1, tail is 0. So now the idea is you have an infinite coin toss where the probability of heads is 1. So we have infinitely many Bernoulli trials, right? So and then you ask this very simple question: how many trials should I do until I observe my first heads? Right? This is geometric. Right? What is the probability that I get heads in my first trial or second trial and so on? Right? So that's the construction of geometric. So if theta is like really, really small, right, then you will wait for a very long time with a high probability, right, until you see your first heads. Yes. So we'll come back to this. And the point of here I'm trying to make is geometric probability mass function looks like this, right? It's theta. So it's theta to the power of, say, x, and then 1 minus theta. So I weight x times, or the other way around, whichever, doesn't matter. So then it has this kind of a shape, right? The mass function decreases like this. And of course, this goes to infinity, right? And then the sum of these things, it's the geometric series from calculus, pre-calculus. That's why it's called the geometric random variable. Exponential is just a continuous version of this. I'll get back to this. It's exactly 2 p.m. now.